Welcome back, penultimate lecture of the course. Most of you should be happy that this course is coming to an end. Happiness can be you are getting rid of something, happiness can also be that you have learned something. Please send your feedbacks to me, I will be happy to receive constructive feedback. Do not really say that this course was rubbish, I did not understand. I am not expecting for something like that. I have tried my level best to make you learn a new thing in simple terms. So, please be constructive in your feedback, that will really help maybe myself to design the course in future in a different way, or maybe to deliver the lectures in a slightly different way, or to even change the interaction platform or something like that. Anyway, coming to topic, the last topic I would like to take up is another form of instability, what is known as elastic contact instability. The word elastic should remind you of elastomer, because you have already seen the use of an elastomeric thin film in the context of replica molding. And yes, the films that we use in these experiments are again those Selforganized 184 films, which are elastic films. So, these are cross-linked films. So, only difference is you would like to take thin elastic films and these films are not as thin as the films you require for duetting, because as you will soon see, the physics, though it is triggered by the van der Waals forces, is not due to the interfacial interactions across the two interfaces of a film. Therefore, the film thicknesses that are taken are in fact quite thick if you compare them with the thickness of duetting films. These are in the range of few micron in fact. Okay. So, in fact, there is a problem if you go down below 1 micron, there is in fact some problem which we will discuss. So, what you typically do is you again take Selforganized 184, but you do not pour Selforganized 184 the way you would otherwise have poured for, let us say, something like replica molding, because that will lead to very thick films, very millimeter thick films. And I mentioned while I was talking about spin coating, that if you take a very viscous polymer or a material and then even if you rotate it at a very high RPM, it often does not flatten out. So, spin coating, even spin coating will not give you very uniform films. So, what you typically do in order to create these films, you take Selforganized 184, but you dilute it in a regular solution, a regular solvent like N-hexane or N-heptane or chloroform, which are good solvents for Selforganized 184, then do a spin coating. Of course, after you have spin coated, the solvent is evaporated, the Selforganized 184 mix is created again by mixing part A and part B. So, right after spin coating, in fact, you do not have an elastic film. Why? Because the part A and the part B or the cross linker has not really triggered the cross linking of the oligomer or part A. So, the spin coated films are typically annealed in an oven. That is what you know, what you typically do to cross link your film. It is annealed in an oven, and then the films are ready for performing the experiments. So, look at the name, it says it is contact instability. So, contact with what? In fact, this is the experimental setup. It is in fact you have this elastomeric film, you take another rigid contactor, and these two, in fact, the instability manifests when the contactor comes in very close contact with the film. So, it is essentially a contact problem of a soft material, and therefore, this instability class is very general. And what happens is, so what you have is a film which is coated on a substrate, of course. This film now, if you compare with what you have already learned in case of duetting, there is zero disjoining pressure, or effective interface potential within the film is 0, simply because of the fact that the film is too thick. As I mentioned, the film thickness is of the order of few microns, and therefore that is not the concern. But the issue is that you have another rigid substrate which is progressively coming in contact with to the film. I will sort of take help from or use the AFM literature to use a word approach. That's the easiest way to describe the situation, isn't it? A rigid surface is approaching a soft elastic film coated on another surface. So what is the final configuration? Final configuration is like if you have this film, another surface is approaching, they will simply touch, which is fine. But please do not forget, when the two come in conformal contact, the separation distance is 0. Of course, in one of the settings you have read even at contact their separation distance is not 0, it is d0, and which is 0.158 nanometer. For all experimental purposes or all practical purposes, it is quite logical to assume the separation distance to be 0. Does it ring a bell? The question is that, well, indeed these two are coming in contact from a far or a large separation distance, and they come in contact. But before they come in contact, the contactor and the film in fact undergo through a separation distance where the separation distance is below 100 nanometer. And does it trigger a bell? And yes, that is where the critical question is. So if you sort of rapidly bring your contactor in contact with the film, there is a possibility that you might miss out the evolution physics. But suppose if the contactor is close enough to the film and you are bringing it very slowly, then what happens is when the separation distance is below again that critical range of 100 nanometer, there is now active VDW interaction, van der Waals interaction between the film and the rigid contactor. Just the way in the context of an AFM, your tip was chosen to be of a cantilever which is soft enough to deform to van der Waals forces, it turns out that these soft elastic films are also adequately soft and they deform subjected to these van der Waals forces. Now, what we are seeing? We are seeing the van der Waals interaction of two objects through air. There is nothing inside, right? And we all know that van der Waals interaction in air is always attractive. Therefore, the contactor in fact exerts attraction on the film surface. Therefore, the film surface tries to jump and go in contact with the contactor surface, an analog of jump to contact. Up to this point there is no problem, but look into the material property of the film. It is not a liquid, right, heated beyond its glass transition temperature. It is a cross-linked elastomer. So what happens is, as part of the film, I will just draw an exaggerated view, as part of the film jumps and comes in contact with the contactor, it leads to significant stretching of the cross-linked matrix, and therefore the cross-linked matrix on the other hand tries to pull it back. So there is now a competition again. In case of dewetting, we talked about a competition where the surface tension tries to stabilize the film and your disjoining pressure try to destabilize the film. Here again, this disjoining pressure was originating from van der Waals forces. Here again, the van der Waals forces are trying to destabilize the film. Here the only form of destabilization is it is trying to come in contact quickly with the film. However, because of the material property, because it is an elastomer, because it is a cross-link film, the physical crosslinks present within the matrix in fact tries to pull back and oppose this conformal contact, or the film surface moving towards the contactor, which is exerting attraction. More importantly, as it sort of forms this type of contacts, there is in fact significant amount of elastic stresses that remains stored within the matrix. Do not forget it is an elastomer, and the easiest example to remember about an elastomer is a rubber band. So, you stretch it, it remains stretched as long as your hands are active. That means that as long as you are applying force from outside to perform the stretching, it remains in stretch configuration. But the moment you withdraw the force, it will restore back to its original configuration. Keep that in mind, I will talk about it. Now, of course, even after achieving this configuration, if your contactor continues to come in close proximity, what happens is the strength of the interaction between the substrate and the film, the strength of the interaction between the contactor and the film increases, and therefore, you see more fraction of the film coming in contact with the contactor. I hope you have understood what I have tried to explain. If not, you see this cartoon once more. So, you have a contactor which is coming in contact with a flexible soft elastic film, and before they come in complete conformal contact, there is a zone where the separation distance between this film and the contactor is again in the range of that 100 nanometer bracket. Therefore, there is active van der Waals interaction between the two, and that leads to some sort of self-organized instability structures on the film surface. This is a real time image taken under a microscope. So, what you have is again the situation we showed, that here is the contactor, this is coming in contact with the film, and you are now observing from the top under with a microscope, optical microscope. So, see what is there, what happens. So, first what we see is that initially we had a flat film and the contactor was far away. You see that some structures are appearing in the form of isolated columns, and the contactor is still approaching, and suddenly you see the whole area gets filled up with some structures. And what is the nature of the structure? It is sort of a bicontinuous labyrinth structures, and I will come back to that. But if you even beyond this stage, if you continue your approach, you now see that those labyrinths have transformed mostly into isolated holes. I will repeat this video again for your convenience. See, the initial stage of approach is manifested with the formation of isolated pillars. Then these pillars transforms into bicontinuous labyrinths. See, this is where the bicontinuous labyrinths form, and just like in dewetting, you did nothing but to simply thermally anneal the film and everything was self-organization. Here also you are doing nothing but to bring in a rigid contactor. So, the rigid contactor in fact exerts external force to the system. So, the fundamental difference in this form of instability with dewetting type instability is, in dewetting the energy penalty for the system to evolve was available within the film itself in the form of excess free energy. Here the films are thick, so therefore, there is no question of excess free energy. Therefore, in order to destabilize a film, you need to supply some energy from outside, and that force is being exerted in the form of van der Waals force by the contactor, by the approaching contactor. Anyway, as the approach continues, you see a complete formation of these bicontinuous labyrinths, and even beyond this stage, further approach in fact leads to formation of isolated holes. So, what are the things we observed? One important thing is what is related to the physical nature of the films. What I mentioned, that as some parts of the film in fact goes and touches the contactor, the other part sort of pull it back, and that is why you saw some such sort of very closely packed patterns, and that is because as some areas go in contact, the other areas pull down, and that is related to the elastic nature of the film. And this in fact leads to undulations on the surface which are like this, which is in clear contrast to duetting, where the wavelengths were much higher, and therefore this form of instability is called the shortwave instability. Another important thing to realize that this instability occurs entirely in the solid phase. There is no flow of liquid like what we saw in duetting. So, there is no flow of liquid, and it is purely solid state deformation of the completely cross linked elastic film. But there is something more to that. What you see is the very fascinating aspect, again from the standpoint of patterning, that simply by varying the intersurface separation distance, you are now changing the morphology of the instability structures from pillars to some bicontinuous labyrinths and eventually to some holes. More interestingly, one observes that for a particular thickness, so this transformation occurs as you vary the film thickness, and more interestingly one sees that within errors, of course, as the film continue, the substrate continues to approach the film, the fractional area goes up. But more interestingly, the periodicity of the structures, what is periodicity here? In fact, the structures are random, they are isotropic, but one can do an FFT and find out the periodicity of these structures from there. The periodicity of the dominant wavelength of instability of the structures are roughly the same. In fact, there has been significant amount of theoretical work also in this particular area, and which shows for this type of instability, the periodicity of the structure, the dominant wavelength of the structures scales as 3 times the film thickness. It is a shortwave instability, therefore, it is only, so one can argue that lambda is of the order of film thickness, and the prefactor, exact prefactor is 2.96, which is theoretically found, or it is simply lambda equal to 3h. So, this is exactly what is shown in this particular plot. So, if you plot lambda versus h in a linear scale, you get a slope which corresponds to which is equal to 3. In fact, if you look into the symbols, something very interesting is there, and that is that this scaling relation is valid for all the morphologies. So, you have cavities, columns, labyrinths, and more importantly, it is independent of the exact elastic modulus of the film. So, you need to have a fully elastic film, but whether you have added 5% crosslinker or 10% crosslinker or 15% crosslinker, the scaling relations do not change. There is a lot of very high end theoretical studies which has already taken place, but which I will not include for discussion here. So, we will understand that if you have an elastic thin film which is coming in contact with a rigid surface, you see a morphological evolution, that is one part of it, and the evolution is in the form of, let us say, pillars, then bicontinuous labyrinths, and then eventually holes. More importantly, not only it does not depend on the exact elasticity of the film, it also is independent of the surface energy of the contactor, independent. Okay. So, these 3 pictures in fact tells you something very interesting. So, your generic morphology remains the same, you vary the initial film thickness, you again see this labyrinths, but what you see, the width and the periodicity of the labyrinths have simply gone up. That is very interesting. So, you can create bigger and smaller structures by simply varying the film thickness, but again the problem is these structures are random, and therefore, from the standpoint of patterning they have virtually no application. There is in fact an additional complexity, and the complexity is when I gave you the example of a rubber band, that is, this is after all an elastic film. So, when it is in proximal contact proximity of the contactor of course you see these structures, right, but when the contactor is withdrawn, because if you would like to use these patterns for some other application, let us say for fabrication of hydrophobic surfaces or something like that, when the contactor is withdrawn, it is an elastic film. So, the deformation that has been caused at the surface, it is stored in the form of elastic deformation of the matrix. So, simply as the contactor is withdrawn, the film will revert back to its initial flat morphology, and therefore, one must understand that the instability contact instability structures are transient. So, that is in fact one of the hindrances for using this form of instability for making some permanent structures. But that also opens the avenue for me to just mention briefly one more thing. So, here you see that these three sort of cartoons or snapshots gives you an idea that the film, the contactor is approaching the film, then it is in contact, and you now know that depending on the separation distance which you may control, in fact the morphology will be either pillars or bicontinuous labyrinths or whatever. You know that this approach sequence, the morphology changes. So, a very pertinent question to ask at this point is there a morphology transition during the debonding sequence also? Like while we approached, we saw initially the pillars came, then the bicontinuous labyrinths came, then the holes came, and then eventually the two came in complete conformal contact. The question to ask is, during debonding, does it happen like that, or something else happens, or they simply detach? And it turns out in debonding one sees an exact opposite. So, this is an important observation. One observes exact opposite sequence during debonding. More importantly, so one sees the holes first, then the labyrinths, then the pillars, but most interestingly, in fact there is in fact a hysteresis. So, the separation distance at which the two comes in contact, if this is the separation distance where this is the contactor and this is the film where the first contact is established, during debonding one observes that the films are sort of stretched before they snap off. So, H2 before snap off is greater than H1 at which contact is established. So, that is in fact, there is in fact a, this is what is referred to as the bonding debonding hysteresis. Anyway, so if one wants to use this technique as some sort of a patterning technique, the first necessary condition is to somehow freeze the structures, and there one can in fact take help of a bit of chemistry, because this is PDMS, polydimethyl siloxane. So, it contains the SiO-Si backbone. So, it turns out that if UV light is shined on this particular film, a thin layer of oxides of silicon in fact form over the film surface, and that is stiff enough that prevents the relaxation of the film, and therefore, you can make the patterns permanent. And as you can make the pattern permanent and remove the contactor, you can, that is evident because now you can do an AFM scan, because in presence of the contactor, of course, you can't do an AFM scan. So, one of the problems, one of the limiting factors, what is sort of a problem in utilizing this technique as a viable patterning technique is eliminated, that you can make the patterns permanent. What is the second problem? Second problem is obviously the structures are random, and therefore, can something be done to make the structures aligned? So, here the destabilizing field is in fact the contactor. So, it is very logical to assume that if one takes a patterned contactor, right. So, the pattern, let us say the contactor itself, let us say, is in the form of a grating. Then one would typically expect that areas of the film below the stamp protrusions will exert. So, there can be a separation distance where areas of the film below the stamp protrusion would exert some force, or the van der Waals force over these areas will be active, and in other areas the van der Waals force will not be active. And it is therefore logical to sort of expect that one can in the process get a positive replica. Well, it turns out that indeed the elastic instability patterns can be aligned in this approach, but one gets something much more novel and much more exotic than a positive replica, and that is what exactly what I will discuss in the last lecture of this course. Thank you.